Can an 8 billion parameter model running local agent skills truly replace a 400 billion parameter behemoth equipped with the same tools? For years, the consensus was simple. Bigger models always win. But as skill engineering and agentic scaffolding mature, that consensus is fracturing. A skill is not just a prompt. It is a structured environment containing tools, deterministic verifiers, dynamic memory, and iterative search loops. The financial incentive is staggering. Running an 8 billion parameter model locally can be over 100 times cheaper than querying a 500 billion parameter model. When we plot model parameters against accuracy, raw performance follows a logarithmic curve, but adding structured skills shifts that entire curve upward. Notice how a small 8 billion model with skills reaches 80% accuracy, rivaling a raw 400 billion model. But what happens when both have skills? To understand if small models can replace big models, we must define the effective performance equation across parameter count, test time compute, and skill fidelity. Small models often fail when operating unassisted because their internal representation capacity is bounded. But structured skills act as an external cognitive exoskeleton. In this technical breakdown, we will evaluate architectural foundations, empirical benchmarks across math and coding, and the fundamental failure modes where small models break. Act 2. Architectural foundations. How skills offload cognitive burden from transformer weights into external execution environments. In a standard large language model forward pass, intelligence is strictly bounded by single pass token prediction. All computation occurs in a single linear forward sweep. Skill engineering transforms this single pass into a dynamic state loop. The model emits actions, observes external feedback, and iteratively converges on correct answers. This creates a direct trade-off. You can either bake intelligence deep into parameter weights during pre-training or reconstruct it dynamically at test time. Consider quantizing a model down to 8-bit or 4-bit precision. Weight resolution drops, but skill scaffolding can compensate for precision degradation. Test time search expands the reasoning tree. Instead of predicting one token sequence, the small model explores multiple candidate paths using Monte Carlo tree search. Mathematically, total inference compute equals token generation cost multiplied by candidate evaluation depth. Test time search turns small models into high compute reasoners. By allocating up to 10,000 additional flops at inference time, an 8 billion model can traverse search spaces previously accessible only to massive weights. However, parameter width imposes a fundamental ceiling on intrinsic representation capacity. No amount of prompt engineering can generate knowledge not encoded in weights. Small parameter models suffer from instruction fatigue, distribution gaps in obscure domain knowledge, and rapid error accumulation across long loops. Act 3. Empirical benchmarks. How small models with skills perform against unassisted and assisted frontier models in real-world tests. Let us examine software engineering benchmarks like SWE-bench. A bare 8 billion parameter model resolves fewer than 5% of complex issues. Now equip the 8 billion model with a coding agent skill containing an AST parser, unit test verifier, and repository search. Resolution jumps dramatically. Remarkably, an 8 billion model with skills beats a raw 400 billion model. But when the 400 billion model gets the same skills, it reclaims dominance. This reveals the asymmetry of skill utility. Skills provide a much larger percentage uplift to smaller models, but frontier models maintain a higher ceiling. Consider self-correction loops. When a small model generates flawed code, can it fix its own bugs during execution reflection? Without an external verifier, self-correction fails on small models. If a model lacks the capacity to solve a task initially, it lacks the capacity to critique its own reasoning. This is why external deterministic verifiers like compilers, math solvers, and linters are crucial for small models. They replace flawed internal self-critique with absolute truth. Next, let us look at mathematical reasoning benchmarks like GSM-8K and MATH. Reason distillation, as seen in DeepSeek R1, embeds reasoning traces into small models. By fine-tuning an 8 billion model on distilled reasoning tokens, it learns latent step-by-step verification, multiplying its effective skill execution fidelity. However, long-step agentic execution introduces probability decay. If a small model has a 90% tool accuracy per step, success drops exponentially over n steps. Notice the massive difference. An 8 billion model with 90% step precision has only 34% task success over 10 steps. Small errors compound rapidly. This decay leads to classic small model agent failure modes: schema hallucination, goal drift, and infinite retry loops. Let us visualize tool call fidelity. As prompt context grows, small models struggle to maintain strict JSON schema compliance. Act 4. Economics and system architectures. Analyzing financial trade-offs, edge local deployment, and hybrid router pipelines. Let us examine hardware resource demands. An 8 billion model in 4-bit precision requires under 6 GB of VRAM, running on standard consumer GPUs. Local execution offers zero data leakage and eliminated cloud network latency, making small models highly attractive for enterprise privacy. Instead of forcing a single model size across all tasks, modern systems deploy dynamic model routers. Simple queries go to small models. Complex edge cases route to frontier LLMs. Another emerging design is mixture of agents, where multiple specialized small models collaborate, verified by a single aggregator model. Selecting between a pure frontier model API and a custom small model skill harness comes down to operational cost versus engineering maintenance overhead. Act 5. Synthesis and final verdict. Mapping out the definitive boundary where small model skill systems succeed and where they fall short. To synthesize our findings, let us plot task complexity against output determinism. This matrix reveals exactly when small models with skills can replace frontier LLMs. Small models plus skills fully replace frontier models in bounded domain tasks with hard deterministic verifiers, such as local code linting, database querying, and structured extraction. However, frontier models remain essential for open-ended synthesis, multi-file architectural refactoring, and tasks where no external compiler exists to provide feedback. Skill engineering is not a substitute for fundamental weight intelligence. Instead, it is a multiplier that shifts the efficiency curve across all model tiers. The conclusion is clear. Small models combined with skills do not eradicate frontier LLMs. They redefine the Pareto frontier of practical AI deployment. Thank you for watching. Subscribe to Simple C for more deep dives into AI architecture, skill engineering, and local agent development.